All right, so let's just start by reviewing what we learned last class regarding our reactions of alkynes. So take a second and give me the products of these two reactions here. Actually, I lied. I'm going to change this first one around ever so slightly to make a point here. I'm going to make it 1 carbon longer. Oh, crap. Whatever. We'll leave it there. All right, so we're going to see these addition reactions, right, where the HCl gets added to that pi bond. If I only have one equivalent of the HCl, then I will get an alkene product, okay? Because neither one of these carbons is more substituted than the other, I'm going to have to be good and draw both products here. So here's my blue carbon. Here's my red carbon. We got an alkene. Okay, so I'm going to draw one where the chlorine is coming off of the blue carbon, and one where the chlorine is coming off of the red carbon. Okay, but these would be the major products because I had a, and actually let me draw in my hydrogen explicitly. Our major product is the trans addition. But remember, because of the stereochemistry of our alkenes, we could also have the cis addition product. Oops. Where the chlorine and the hydrogen are added to the same side. All right, so if I perform this reaction with this particular alkyne, I'd get a mixture of these 4 products. 2 of them would be present in a larger concentration, what we would call the major product. And two of them would be our minor product, the cis addition product. Okay, and remember that's just because the cis addition product is just less stable. You got big bulky groups on the same side of that double bond. All right, I kind of made this more difficult than I meant to, though. All right, but yes, because neither of these are more substituted, we got to have a mixture of both, with the chlorine is added to the blue carbon and the chlorine is added to the red carbon. But then we also have these two stereoisomers to worry about, two sets of stereoisomers to worry about. The major product is our trans addition, and the minor product is our cis addition. All right, I'm going to choose a slightly simpler example here to make some notes on so I can actually fit. Take that group off of there. All right. Now we don't have to worry about stereochemistry. Cool. All right, so my product here after my one equivalent is just going to have one chlorine on there. After I add two equivalents, it's just gonna again react with that pi bond. And importantly, I'm gonna see a chlorine on the same carbon, both chlorines added to the same carbon. That blue, more substituted carbon. Okay, for these reactions here, again, we have a mechanism. It's the exact same as our other hydrohalogenation reaction with alkenes. We have a carbocation intermediate. Because the chlorine is added to the more substituted carbon, we would say that these are regioselective reactions. And we call that more substituted carbon Markovnikov reactions. All right, and stereospecificity is what we went over in the first example here. Where we have both a major and a minor product. The major product is the trans addition product, whereas the minor product is the cis addition product. All right, so then let's do a similar set of reactions here, but for our halogenation reactions. Get our little summary cheat sheet for those halogenation reactions. Bless you. right? So when we get just one equivalent of our halogen, we will break one of those pi bonds, do an addition to one of those pi bonds. That will give us an alkene product, okay? And remember, the mechanism for these reactions, just like with alkenes, are those cyclic intermediate mechanisms. Okay, and because of that, we only get one stereoselective product, right? Because of that cyclic intermediate, these chlorines are necessarily going to be added to opposite sides, so we will always have only the trans addition product. There's no mixture for this type of mechanism here. And then the other thing that's nice about these reactions is because you're adding a chlorine to either side, you're adding the same thing to either side, there's no regioselectivity to worry about. Okay, and if you have two equivalents of your halogen, then you will simply just have this reaction occur twice, putting two chlorines on either carbon. All right, so again, if we're going to color either side of our triple bond here, the carbons on either side of our triple bond. Again, we're adding the same thing to both of them. With only one equivalent, we get an alkene product, and we only get one because we're going to specifically have the trans addition product. If we have two equivalents of chlorine, we're just going to get two chlorines added to those carbons. All right. We also talked about the hydration of alkynes rather. The first was mercury catalyzed. The second was a hydroboronation. All right, so let's take a second and tell me what the products of these reactions would be. Mercury catalyzed means that we have mercury sulfate, sulfuric acid. Hydroboronation is with boron. Okay, both of these are hydration reactions. Take a second and see if you can't tell me what the product of these reactions are. All right, so remember these reactions, similar to hydration of alkenes, they did first produce alcohols, what we called enols, but then remember enols will tautomerize into either ketones or aldehydes. So those are the products of our reactions, of our hydration reactions of alkynes, either ketones or aldehydes, depending on your alkyne. Okay. So in the case of our mercury catalyzed, it's going to put the oxygen on the more substituted carbon, so on the blue carbon. Okay, and again, it's going to tautomerize into a ketone. If you did a hydroboronation reaction, going to get something similar. But remember, boron's claim to fame is that it sticks that oxygen on the less substituted carbon. So in this case, our red carbon. And so that's where my carbonyl bond will form. All right, and remember, when your carbonyl bond is on the very end like that, we don't call it a ketone, we call it an aldehyde. All right, so let me scrunch this up so we can make our notes here. Cool. All right, so for this reaction, for these reactions, we actually don't have a mechanism for the mercury or the boron catalyzed part, but what we do have a mechanism for, the mechanism that we do have to know, is that tautomerization. From the enol to the ketone or aldehyde. That's what we got to know. In terms of regiospecificity, all right, these reactions are regiospecific. That's the difference between the two of them, right? So mercury puts it on the more substituted carbon. That's our Markovnikov. The boron puts it on the less substituted carbon. So that's the anti-Markovnikov. And again, that's the same phenomenon we saw for alkenes. Our mercury catalyzed hydration reaction was Markovnikov, and our boron catalyzed hydration reaction was anti-Markovnikov. Okay, and then the nice thing about these carbonyl products, we don't have any stereoisomers to worry about. No stereospecificity. Okay, so this summarizes the reactions that we learned about last class. Similar set of reagents that we've seen before, our hydrohalogenation, our halogenation, and then our hydration reactions. All right, all addition reactions, because just like alkenes, alkynes have those pi bonds that we can add to. So we got another set of very similar reactions to go over here. Our hydrogenation reactions. Okay, so let's take a alkyne, a triple bonded compound. All right, we're going to look at a few different hydrogenation reactions. The first one is the same as with our alkenes. where you use hydrogen gas over that solid palladium catalyst. Okay, this particular reaction here is like industrial strength hydrogenation reaction. I don't know if you've ever heard about hydrogenated fats, but that's where like candy companies figured out that they could take good healthy oils that were easy to get from vegetables and turn them into bad tasty oils called saturated fats by performing this process here, by turning all the double bonds in those fats into single bonds. Turns out fats with double bonds are good for you, fats with single bonds are bad for you. Okay, so this thing happened, they figured out this process and it works very, very well. So much so that if you have an alkyne, it will just fully reduce that alkyne all the way to an alkane. All right, there's no way to sort of stop it in the middle at the alkene step. It just blows right through and hydrogenates both of those pi bonds in one shot. Okay. So this would be a great way to turn an alkyne into an alkane. All right, but outside of the candy industry, from an organic chemist standpoint, that's not very interesting. I mean, what like, okay, great if we want alkanes, but like, they're not a very useful functional group, right? We can't really do much with alkanes other than explode them. And alkenes and alkynes burn just well. They combust just well. So what if we want to stop at that alkene step? Well, they developed a catalyst that's very similar to this palladium catalyst, but what's named after this dude Lindlar. Lindlar's catalyst. It's kind of just a modified palladium catalyst. Okay? But this will indeed give us an alkene product. Okay? So how this set of reagents looks is, again, you use hydrogen gas, but over, they just spell out the name Lindlar. Okay, and again, we're going to get an alkene. So this is a way to reduce a triple bond that stops after that one addition. Okay, but again, Lindlar's catalyst is very similar to a palladium catalyst in that it's a surface catalyst. So let's think here. Let's remember what happens. We have this surface. Our hydrogen gas comes and binds to that surface. And then that triple bond's going to come, and those hydrogens are going to get added. Are those hydrogens going to get added to the same side of that triple bond or opposite sides? They're going to be the same side. So this would be a way to produce a cis alkene. All right, because again, those bonds are added to the same side. What we call it a cis addition. Right, but what if we want the other stereoisomer? We're going to have to use another method. This uses either sodium or lithium in ammonia. Okay, so if we want to take our alkyne then we can get a transalkene using this method. All right, and I'm always ragging on sodium for not doing anything in chemical reactions, but to be clear, this isn't the sodium ion. This is actually sodium metal here. And solid sodium metal's entire job in life is to get rid of that electron and become the sodium ion. And so that's exactly what happens here. We're not going to go through this mechanism, but it does proceed through a radical where that sodium donates one electron to this compound and kind of blows everything up. Okay, so again, Lindlar's catalyst will help us create a cis alkene. This other method is how we create a trans alkene. Okay, so we have 3 different hydrogenation methods for our alkynes. The first just fully reduces all the way to an alkane. The second will stop at that alkene step but produce a cis alkene because those hydrogens get added to the same side. And the last method is how we can produce a trans alkene where those hydrogens get added to opposite sides. Okay, for these reactions we have no mechanism. We don't really know how the electrons are moving. Are we going to have any regiospecificity for this reaction? That's stereochemistry though, so regiospecificity, no. Why not? Same thing to both sides, exactly. So we also don't have to worry about any regiospecificity. But yes, absolutely. The whole shtick between these different reactions is they are stereospecific. Lindlar is the cis addition. The sodium and ammonia, the trans addition. Okay, so first of all, let me just stop and sort of emphasize the importance of something real quick. Let me grab this guy. All right, so what we just learned how to do was to convert an alkyne to an alkene. Right? Again, this particular method here was using hydrogen gas and Lindlar's catalyst. Okay? But let's note, we also know how to go the other direction as well. This is another reaction that we learned last class, where you first take an alkene, do a halogenation reaction to it first, and then second follow that up with a strong base, and you can prepare an alkyne. All right, so we know how to go both directions here. So this is going to be very important for our synthesis strategies. Not only do we know how to make an alkyne into an alkane, but an alkyne into an alkene, but vice versa as well. We know how to make an alkene into an alkyne. All right, so let's just take a second to make a cheat sheet for that preparation of alkyne reaction. Again, a reaction that we studied last class, but just so we can sort of summarize everything here. Okay, again, you first do a halogenation reaction, just like we studied last chapter. All right, but then you do what's called an elimination reaction, something that we did in lab actually, but haven't talked about here in lecture explicitly. And that will create an alkyne. All right, we actually do have a mechanism for the first step, but not the second step, and actually we will next chapter, but we're not there yet. So let's just say no mechanism, not yet at least. All right, there's also no regiospecificity. And because our product is an alkyne, and alkynes just don't have stereochemistry, we don't have to worry about any stereospecificity either. All right, we just definitely want to keep this one in mind as a very important reaction because, again, we know how to transfer one functional group into another one. That's always a powerful move in our organic chemistry synthesis. All right, and then our last familiar reaction for alkynes, we actually got two more, but the last one that uses some similar reagents here is what's called an ozonolysis reaction. We saw this before with alkenes. What occurs is what's called an oxidative cleavage reaction. Okay, so again, we've seen these reagents before. It's ozone, O3, in dichloromethane at very cold temperatures. All right, and again, just like we saw with alkenes, it's going to chop this molecule in half, right at that triple bond. All right, just like we saw before. So we're going to, again, like literally chop this molecule in half. So we're going to break it into one fragment that is these 3 carbons and another fragment that are these 2 carbons. Okay, and before, if you remember, what we did was we literally like took this and said, chop it in half, separate these parts, and we're going to put an oxygen over here and an oxygen over here. Okay? That doesn't really make sense with alkynes, though, because we have a triple bond, and we can't have a triple bonded oxygen. All right? So what instead we see is something very similar. Again, it's going to chop that bond in half, but instead of adding just one oxygen, it's going to add 2 oxygens and create what we call a carboxylic acid. So again, I get 1 3-carbon carboxylic acid, and then my other fragment, is 2 carbons, and again, another carboxylic acid. Okay, so this is where my green carbons made it off to. Okay, so alkenes and alkynes will both undergo oxidative cleavage reactions. For alkenes, you get a carbon-oxygen double bond. For alkynes, you get a carbon-oxygen double bond plus 1 more carbon-oxygen single bond to produce carboxylic acids. Okay, for these reactions, we have no mechanism. We don't know how ozone got so good at karate. Okay, we also don't have to worry about any regiospecificity or stereospecificity. All right, so the last reaction that we're going to cover for our alkynes is something that's very unique to alkynes. It's not something that's shared by our alkenes, which is rare. Most of these reactions are kind of just duplicate from last chapter with some tweaks here and there to account for the triple bond. Okay, so this one is going to be unique to alkynes, and it's going to have everything to do with how easy it is to remove a hydrogen from an alkyne compared to an alkane or an alkene. All right, so I want to specifically look at the carbon-hydrogen bond on these different functional groups here. Right, so looking specifically at these bonds here. Okay. Turns out that these bonds have very different strengths depending on the functional group. And we actually have this way, this measure, this quantitative measure that we can look at to compare how easily a compound donates its hydrogens. What constants page did we have where we were looking up values and comparing compounds in terms of how easy they donated hydrogens? pKa's, exactly. So let's look at the pKa's of these various functional groups. Go back to our handy dandy pKa table. All right, the absolute last entry on your pKa table are alkanes, right? Carbon sp3 hybridized carbon-hydrogen bonds. And below that is an sp2 carbon-hydrogen bond, an alkene hydrogen. And that's quite a bit less, 44 compared to 60, but still a really large number. All right, so this is 60 or greater. This is around 44. Okay, for alkynes, we scroll up and we see that these are around 25. Okay, which is still a pretty big number. In no way, shape, or form is this like a strong acid or anything like that. Right, so these were 25, but considerably less than the other ones. So to put that in perspective, an alcohol tends to be around 16, water tends to be around 16. So by no means are these like great acids at all, but if we have a strong enough base, we can remove that hydrogen. Okay, and we need a pretty freaking strong base. Sodium hydroxide, our go-to strong base, is not strong enough. We need a very strong base. So our very strong base that we use is what's called an amide ion, a deprotonated nitrogen. Okay, so not oxygen with a negative charge. This would be a strong base. A hydroxide ion. Okay, but that's not quite strong enough. An amide ion is. Okay, so then everybody take a second. I have this very super strong amide ion here. Everybody take a second. Draw me my acid-base mechanism here and my products for this reaction. All right, so that base is going to reach out and steal that proton, breaking that bond right there. Okay, so I get NH3, which I don't really care about. All right, but then my other product here, now I'm missing that hydrogen. What else is this structure missing? Is it a positive charge? Not a positive charge. Why a negative charge? Because I'm starting with a negative charge, right? So I know I'm going to have a negative charge in my product. And indeed, where did this pair of electrons that was in that carbon-hydrogen bond, where did that go? To the carbon. That is now a lone pair sitting on that carbon. Okay, this thing here, we give a special name. This is what's called an acetylide ion. All right, and an acetylide ion is a great nucleophile. A good electron-dense, got a lot of negative charge nucleophile. Okay, so these things can react with electrophiles. So one that we talked about, the one that we're going to sort of stick with here, it's an alkyl halide. These are electrophiles because they have that polar bond, right, which means that carbon has a partial positive charge, but importantly, they also have a good leaving group. So the nucleophile is going to do what nucleophiles do. Do nucleophiles attack or do they get attacked? They are the attackers. And that's indeed what's going to happen. It's going to attack my electrophilic carbon, right? Can't stop there though, or carbon has too many bonds. So in the process, it kicks off that leaving group. Okay, so everybody take a second and draw me the product of this step here. Way too big. How many carbons are in our product? 4, right? So we started out with a 3-carbon alkyne, and now we have a 4-carbon alkyne. Right? So we just created a larger, well, starting out with a small, what we would call a terminal alkyne, one where the triple bond is on the very end of the molecule. We end up with a larger internal alkyne. Now the triple bond is in the middle of the molecule, right? So this is just very important to note here that we actually created a new carbon-carbon bond. This is relatively powerful. This is the only reaction that we know about that creates new carbon-carbon bonds. Up until now, our carbon backbone hasn't really changed at all. Who's bonded to who is not changing, right? we now have a method of growing our carbon chain. All right, we went from a propyne to a butene. Okay, and again, it has everything to do with this acetylide ion being a good nucleophile. So we call these acetylide nucleophile reactions. Okay, so just to kind of summarize these reagents all into one step here, we have again, what we call a terminal alkyne. Okay. And we first treat it with our amide ion. And then by an alkyl halide, so I'm just going to use this as Rx. Where R stands for any number of carbons. All right, the one caveat about this alkyl halide here is it has to either be a methyl alkyl halide, as in the case of our reaction that we did previously, or a primary alkyl halide. Secondary or tertiary alkyl halides will not give you this same product. But following those two steps, we'll stick that any number of carbons on the other end of your alkyne. Okay. So for this one, we can note, yes, we have a mechanism. It's an acid-base reaction followed by a nucleophilic attack. All right, but there's no regiospecificity. I mean, that R group's going on the end, but it's got no other choice. And no stereospecificity either. All right, so let's just do an example here. All right, so I'm going to start out with my 1, 2, 3, 4, 5, 6 carbons. All right, but now I'm going to grow my carbon backbone here by adding these additional 1, 2, 3 carbons from my alkyl halide. So I got 3 additional carbons on there that I'm going to draw. 1, 2, 3. And remember that first one we got to draw in a straight line to represent the linear geometry of that alkyne. Okay, so again, just something very important to note that we actually have a way to grow our carbon backbone here. Cool. All right, so now that we got a good bit of reactions under our belt here, can introduce one of the biggest challenges in organic chemistry, which are multi-step synthesis problems. Okay, it's one thing to jump from a reactant to product when you only need one step. It's a kind of a different story. It's a next level challenge when all of a sudden you got a few steps separating these. All right, so I'm going to put down a few problems here, and you guys are going to try to propose a synthesis pathway. What reactions do you do in what order in order to get from reactant to product? right, so what's going to make these problems difficult is they sort of require you to have a pretty good understanding of the different reactions that you covered. Yeah, I mean, when there's only one step, you can sort of have a little bit more context clues. There's no one way to approach these problems. You just kind of got to be a little bit of a detective and find any clues where you can. So in this first one here, something that really big that jumps out at me right away is the fact that my reactant has 1, 2, 3, 4 carbons, and my product has 1, 2, 3, 4 plus 2 more, 5, 6. And there's only one method that we have that creates new carbon-carbon bonds. So I know I'm going to have to use that, all right? So and that method starts with an alkyne, so let's go ahead and do that first. I'm going to use my sodium amide, followed by potassium hydroxide. Oh no, that's not true. Followed by that alkyl halide, which in this case has to be 2 carbons. Doesn't matter which halogen you pick, as long as it's not fluorine. All right, but that's my 2 carbons. So now I'll have grown my carbon backbone. Okay, adding those 2 on there. So 1, 2. Cool, but I'm not there yet, right? I still got at least one more step to do. Do we have a way to turn alkynes into alkenes? Yes, so this is also something that we know how to do. So we can bridge this gap here using one of our hydrogenation reactions. Okay, in this case here, because I get the cis product, I'm going to want to use Lindlar's catalyst. All right, so if I want to do this synthesis here, I'm going to have to do these 2 steps. I'm going to first use this method to elongate my carbon chain, and then I'm going to use Lindlar's catalyst to get my cis alkene. All right, this second one is more difficult, okay, because I don't have quite as obvious of something jumping out at me. And I'm starting with alkenes. We know a crap ton of different things to do to alkenes, right? So it's not like it's going to be very obvious what we should do in this next step. Here we got a ton that we know how to do to alkenes. So it's actually going to be more helpful to look at the product side and to try to think about what methods we have for creating this functional group here. We got a pretty distinct functional group, a ketone. What methods do we have to create ketones? Okay, well, we got 2 of them. Starting with an alkene, we can do an ozonolysis reaction. Those produce carbonyl bonds. Or if we started with an alkyne, we could do our hydration reaction, right, which creates the enol, but then the enol quickly tautomerizes into a ketone or an aldehyde. Okay, well, I'm starting with an alkene, so it might be like, okay, great, then let's just do that ozonolysis reaction. But what's going to happen to my number of carbons if I do an ozonolysis reaction? In my product, how many carbons would I have? I would have less, exactly, because it cleaves that double bond, right? So that'd be great if I was looking for a smaller molecule, but I still have those 4 carbons, all right? So I don't know about this one, probably not. Well, if I started with an alkyne, I could definitely do a hydration reaction to get to this product. Can I make an alkyne from an alkene? Cool, all right? So in this case, it sort of made more sense to try to work backwards because we had less options going from this end than we did going from this end. There's just a ton of different reactions we know how to do to alkenes. Okay, so where we want an alkyne, in the middle here, and then we'll do a hydration reaction. Let me make this smaller. All right, so step one, we're going to make an alkyne by first doing a halogenation reaction and then following it up with a strong base. That will give me an alkyne, check, check. And then we want to do a hydration reaction. Which hydration reaction am I going to do? Mercury or boron? I guess it wouldn't actually matter, huh? But sure. In this case, it's an internal, so it doesn't really matter. But sure, let's do mercury H2SO4. And so then we have a hydration reaction to produce our ketone. Okay, so these multi-step synthesis problems are going to kind of, like, to be dead honest with you, they're going to haunt you for the remainder of your organic chemistry career. They're the toughest of the types of problems because they involve more than one reaction. And all we're going to do is learn more and more reactions as time goes on, right? So again, keeping up with your flashcards or that portion in your notebook where you summarize all your reactions is going to be really helpful. The other pieces of advice, again, is to work backwards. Sometimes that's the most useful thing. Oftentimes, finding a unique functional group is really helpful for knowing what you can do because we only have a few ways to create that unique functional group. All right, and then my last piece of advice is, I think I had already told you guys, I always like to study in like an empty classroom so I could do work on the board, because then it's really easy to make a mistake and just be like, okay, fix that, move on with your life. Sometimes people are terrified to make mistakes in their notebooks. You don't like doing sort of messy work in your notebooks. I get that. I have two notebooks. I have a notebook for messy work and a pretty notebook where I copy everything into, all right? Bottom line is you can't be afraid to make mistakes. If you're stuck, just try something. Let's throw a reagent in there, see what happens. Does that get me anywhere closer to my product, all right? But some trial and error. Obviously, if you look at a problem and you know exactly what to do, fantastic. If you don't know exactly what to do, you don't want to be crippled in fear and not try to move forward at all, right? Just start throwing crap at the wall and seeing what sticks, okay? But yes, these are just going to be a challenge, and they're just going to get a little bit tougher as we go on because we're going to learn more and more reactions. What's up? Of course. Absolutely, yes. Yeah, that's what we're gearing up to here. Yeah, but yes, there will be. As well as in your homework, so you'll have some practice. Cool.